What would you do if you knew the only thing standing between 4 astronauts and a fiery death had already cracked in over 100 places, and the agency responsible for getting them home launched anyway? Tonight, the Orion spacecraft is hurtling back toward Earth at over 23,000 miles per hour. 4 human beings are strapped inside a capsule the size of a large SUV, separated from plasma hot enough to vaporize steel by a heat shield that its own engineers know is compromised. A former NASA astronaut, a man who spent his career studying exactly this kind of thermal protection system, looked at the data and said publicly that what NASA is doing is crazy. He compared it to Challenger. He compared it to Columbia. And he gave the crew a 95% chance of making it home alive. That number sounds reassuring until you realize what the other 5% means. This is the story of the most controversial re-entry in the history of human spaceflight. Here is what you are about to see. The Orion crew module separates from its service module at 400,000 feet above Earth. Completely alone, completely committed. It hits the upper atmosphere at 23,000 miles per hour and executes a maneuver that has never been used on a crewed mission before. A skip re-entry, deliberately bouncing off the upper atmosphere like a stone skipping across a lake. Temperatures on the heat shield climb to 5,000 degrees Fahrenheit, hotter than the visible surface of the sun. The AV-coat ablative material begins burning away, exactly as designed. But beneath that charring surface are cracks. Over 100 of them, documented by NASA's own Office of Inspector General after Artemis 1. And here is the curveball that nobody is talking about. The very maneuver NASA designed to reduce heat load may actually be making things worse for a shield that is already damaged. But we will get to that. First, let's understand how we got here. Look at the map here. This is the Artemis program, NASA's flagship initiative to return American astronauts to the surface of the Moon for the first time since Apollo 17 in December 1972. The program has cost the American taxpayer over $93 billion since its inception, making it one of the most expensive space programs in human history. At the center of this program is the Orion Multi-Purpose Crew Vehicle, a spacecraft designed to carry up to 4 astronauts beyond low Earth orbit around the Moon and back again. And at the center of Orion's survivability is its heat shield. Without it, re-entry is not a landing, it is an explosion. This is Stage 1. The date is April 10th, 2026. The time is just after 8 p.m. Eastern. For the past 9 days, the Artemis II crew has traveled further from Earth than any human beings since the Apollo era. They have looped around the far side of the Moon, the side that faces permanently away from Earth, the side that receives no radio transmissions, no GPS signals, nothing. Complete communication blackout. And they survived it. Life support worked, navigation worked, propulsion worked. Communications worked the moment they cleared the lunar limb and Earth's signal could reach them again. By any measure, the mission to this point has been a success. But now comes the hard part. At 400,000 feet above the Pacific Ocean, the Orion crew module separates from its service module. Watch this on the diagram here. The service module, the cylindrical structure that contains the main propulsion engine, the solar panels, and the consumables, falls away and burns up on its own re-entry path. It has done its job. What remains is the crew module, a blunt body capsule approximately 16.5 feet in diameter and 10.6 feet tall, weighing approximately 22,700 pounds fully loaded. From this moment forward, the crew has zero propulsive capability. There is no engine, there is no thrust, there is no abort option. The trajectory is fixed by physics. The only variable is whether the heat shield holds. This is Stage 2. Orion hits the upper atmosphere at 36,000 feet per second. That is 23,000 miles per hour, or roughly Mach 32. To put that into perspective, a commercial airliner cruises at approximately Mach 0.85. The SR-71 Blackbird, the fastest air-breathing aircraft ever built, topped out at Mach 3.3. Orion is entering the atmosphere at nearly 10 times the speed of the fastest jet ever flown. At that velocity, the air ahead of the capsule cannot get out of the way fast enough. It compresses, and compressed air heats. The shock layer, The zone of superheated plasma between the bow shock and the heat shield surface climbs toward 5,000 degrees Fahrenheit. That is 2,760 degrees Celsius. For reference, iron melts at 2,800 degrees Fahrenheit. Steel melts at around 2,500 degrees Fahrenheit. The plasma surrounding Orion's heat shield is hotter than molten steel. And this is where the skip re-entry maneuver begins. NASA engineers, faced with the compromised heat shield, designed a modified trajectory that they believe gives the crew the best chance of survival. Look at this trajectory diagram. Instead of a direct, steep plunge, the kind of re-entry profile used by Artemis 1's uncrewed capsule, Artemis 2 will execute what aerodynamicists call a skip entry. The capsule dips into the upper atmosphere, generates lift from its angled attitude, and literally bounces back upward before committing to final descent. Think of a flat stone thrown at a low angle across a still lake. It hits the surface, deflects upward, travels further, then hits again and sinks. Orion does the same thing, except the lake is Earth's atmosphere, and the stone is traveling at 23,000 miles per hour. The theory is sound. By spreading the deceleration across a longer arc, peak heating is reduced. Less heat per second means less stress on the shield at any given moment. It is a clever solution. But here is where things get complicated. This is stage 3, peak heating. This is the most critical 8 minutes in the entire mission. The capsule has committed to final descent. The skip has been executed. Now, Orion is punching through the denser layers of the atmosphere, slowing from 23,000 miles per hour to subsonic speeds entirely through aerodynamic drag. There is no braking thruster, no parachute yet, just the heat shield, the atmosphere, and physics. On the forward face of the heat shield, the AV-coat material begins ablating, burning away in a controlled, calculated fashion, carrying thermal energy away from the capsule as it vaporizes. This is exactly what it is designed to do. The problem is what is underneath. After Artemis 1 splashed down in December 2022, engineers noticed something unexpected when they inspected the heat shield. Across more than 100 locations on the surface, they found cracks. Not hairline surface scratches, structural fractures in the ablative material itself. In some areas, chunks of charred AV-coat had completely detached and gone missing. The 2024 report from NASA's Office of Inspector General was explicit. The damage was more extensive than models had predicted, and engineers did not fully understand why it happened. That last part is the most important. It was not just that the shield cracked. It was that NASA could not fully explain the mechanism that caused it, which means they could not be certain it would not happen again, or worse. To understand why those cracks are so dangerous, let's crack open the AV-coat heat shield itself. From this cutaway view, you can see the internal structure. AV-coat is not a solid material. It is a honeycomb. Imagine thousands of small six-sided cells, each one approximately a quarter-inch across, made from fiberglass. Each cell is filled with a proprietary epoxy Novolac resin compound. When this material is exposed to extreme heat, the resin undergoes a chemical transformation called pyrolysis. It breaks down at the molecular level, releasing gases that carry thermal energy away from the surface as they escape. The outer layer chars, forming a protective carbon crust. Beneath that crust, the fresh AV-coat continues ablating. Layer by layer, the shield sacrifices itself to protect the crew. It is an elegant system. For Apollo, it worked perfectly. But here is the critical detail. You will notice in this cross-section that the honeycomb cells are bonded together at their shared walls. When ablation happens unevenly, when one cell burns faster than its neighbor, differential thermal expansion creates stress at those shared walls. That stress produces cracks. And once a crack exists, it becomes a pathway. Superheated plasma does not simply flow around obstacles. It finds the path of least resistance. A crack in the AV-coat surface is an invitation for 5,000-degree plasma to channel deeper into the shield structure, bypassing the protective layer and reaching the underlying aluminum structure of the crew module. You can see just how thin that margin is when you look at this diagram. The distance between the plasma and the crew cabin, accounting for the ablative layer, is approximately 1.7 inches of avcoat at its thickest point, 1.7 inches of honeycomb resin between 4 human beings, and plasma hot enough to vaporize metal. This is the same failure mode that destroyed Space Shuttle Columbia on February 1, 2003. Not an identical mechanism, Columbia's thermal protection system used ceramic tiles rather than ablative avcoat, but the same fundamental principle. A gap in the thermal protection system, plasma channeling through the gap. Structural failure. Former NASA astronaut Charlie Camarda, who worked on the Columbia investigation and has spent decades studying thermal protection systems, looked at the Artemis II data and did not hesitate. NASA definitely does not have the data to show that it's safe, he said. I realized they were using the same flawed thinking and crude analysis tools, similar to Columbia, similar to Challenger. Those are not words you want to hear from a man who has spent his career preventing exactly this kind of catastrophe. Sponsor section, insert here. But here is the curveball that makes this story even more complicated, and it involves the very solution NASA chose to protect the crew. The skip re-entry maneuver was specifically designed to reduce peak heat load, and in that narrow sense, it works. By spreading deceleration across a longer arc, the maximum temperature the heat shield experiences at any single moment is lower than it would be during a direct, steep re-entry. Peak heating is reduced. On paper, the shield is safer. But think carefully about what the skip re-entry actually does to the total thermal exposure. Look at this graph here. The red line is the Artemis I re-entry profile, a steep, direct descent, short duration, high peak temperature. The blue line is the Artemis II skip re-entry, a shallower, longer arc, lower peak temperature. Now look at the area under each curve. That area represents total heat energy absorbed by the shield over the entire re-entry. The blue line's area, Artemis II, is larger. The skip re-entry exposes the heat shield to elevated temperatures for a longer period of time. Instead of one intense thermal spike, the shield endures a sustained thermal soak. For an intact, undamaged heat shield, this trade-off is acceptable. Lower peak temperatures mean the ablation rate is more controlled, more predictable. But for a shield with pre-existing cracks, for a shield whose internal structure is already compromised, sustained thermal exposure is potentially more dangerous than a brief, intense spike. A longer duration at elevated temperature gives those cracks more time to propagate, more time for plasma to find pathways through damaged material, more time for differential thermal expansion to widen existing fractures. NASA's own fix may have introduced a new failure mode into the exact system it was trying to protect. Former astronaut Camarda saw this coming. He told the New York Times he was going to pray that nothing happens. A man with his expertise does not pray for things he is confident about. This is stage 4. The re-entry is in its final phase. Orion has bled off the majority of its velocity. The plasma sheath begins to thin as the capsule decelerates into the denser lower atmosphere. Speed drops through Mach 2, then Mach 1. At approximately 24,000 feet above the Pacific, roughly the cruising altitude of a regional commuter aircraft, the first drogue parachutes deploy. 2 small high-drag chutes, each 23 feet in diameter, snap open and begin stabilizing the capsule's attitude. From this camera angle, you can see the violence of that deployment. The capsule lurches, oscillates, then steadies. At 8,000 feet, the 3 main parachutes deploy. Each one is 116 feet in diameter, wider than a 10-story building is tall. Combined, they generate enough drag to slow Orion from approximately 300 miles per hour to a manageable 17 miles per hour at splashdown. The Pacific Ocean comes up fast. Recovery ships are already positioned within the target zone. Divers are in the water. The capsule hits the surface. Splashdown. The impact generates a wall of white water visible from the recovery vessels standing by nearby. For a moment, nothing moves. Then the hatches are confirmed sealed, the flotation collar is attached by Navy divers, and the hatch opens. 4 astronauts emerge, blinking into Pacific sunlight. The mission is over. They are alive. By any public measure, NASA will declare this a complete success. Administrator Jared Isaacman will point to the modified re-entry profile. Engineers will point to the fact that the crew is breathing. And they will not be wrong. The crew is alive, and that matters more than anything else. But the question that Charlie Camarda asked, the question that dozens of engineers and former NASA employees asked in the months leading up to this launch, does not go away just because the crew survived. Did the modified trajectory actually work as intended? Or did the crew survive in spite of the compromised heat shield rather than because of NASA's fix? The post-mission inspection of the AVCOAT material will answer that question. Engineers will map every crack, every area of accelerated ablation, every location where the material behaved differently than the models predicted. If the damage is significantly worse than Artemis 1, the Artemis 3 moon landing, currently scheduled to put astronauts on the lunar surface for the first time since 1972, will face serious questions. If the damage is comparable or less, NASA will argue that the skip re-entry worked and press forward. The data will decide. But step back from the specifics of Artemis 2 for a moment and look at the pattern. In January 1986, engineers at Morton Thiokol warned NASA that the O-rings on the Space Shuttle solid rocket boosters were not rated for the cold temperatures forecast on launch morning. They were overruled. Challenger broke apart 73 seconds after liftoff. In 2003, engineers at NASA flagged the foam strike on Columbia's leading edge as a potential catastrophic risk and requested satellite imagery to assess the damage. The request was denied. Columbia broke apart on re-entry, killing all 7 crew members. And in 2026, NASA's own Office of Inspector General documented over 100 cracks in the Artemis 2 heat shield after Artemis 1, with engineers explicitly stating they did not fully understand the failure mechanism. NASA flew anyway. The crew survived. But the pattern, technical warning, institutional pressure to proceed, decision to launch, is one that the history of human spaceflight has seen before. And the history of human spaceflight knows exactly how that pattern ends when the outcome is not survivable. The Artemis program is not just a scientific endeavor, it is a statement of national capability, a geopolitical signal to China's competing lunar program, and a $93 billion commitment that creates enormous institutional pressure to maintain schedule. That pressure is real. It is not unique to NASA. Every major engineering program in history has faced the tension between technical caution and schedule momentum. But in human spaceflight, the cost of getting that calculation wrong is measured not in dollars or delays. It is measured in lives. The astronauts who climbed into Orion tonight knew the risks. They are professionals. They accepted those risks with open eyes. The question that history will eventually answer is whether the institution that put them there was equally honest about what it knew and what it did not. We make original videos from scratch and animated by humans. So please subscribe to not miss a